When there's one thing that we want to predict, we use one random variable and its probability distribution. When there's two things that we want to predict, we use two random variables and something called their joint distribution. So recall, if x is a discrete random variable, then the probability mass function is p of little x equals the probability that the random variable capital X equals the value little x. And the cumulative distribution function is capital F of little x, which is the probability that the random variable capital X is less than or equal to the value little x. But sometimes we want to predict two things at a time. Now if we're given two discrete random variables, then we define the joint probability mass function to be p of little x little y, so these are values, which is the probability that capital X equals the value little x and capital Y equals the value little y. And we define the joint cumulative distribution function to be capital F of little x little y, which is the probability that capital X is less than or equal to little x and capital Y is less than or equal to little y. So for example, let's roll a pair of dice. And let x be the number of numbers between 1 and 4 showing. And let's let y be the number of odd numbers showing. Now we've rolled a pair of dice, so we can either have x be 0 if none of these numbers are showing, or 1 if one of them is showing, or 2. We're only rolling a pair of dice, so we couldn't have more than 2 of these. Same with y. We either have no odd numbers, 1 odd number, or 2 odd numbers. So let's make a table for the joint probabilities. Let's put y values up here and x values down there. Y could be 0, 1, or 2. X could be 0, 1, or 2. So how could we possibly have x equals 0 and y equals 0? So I guess all the numbers we roll are going to be 5 or 6. And they're all going to be even. So I guess that can only happen one way. If we get 6, 6, we don't have anything in the 1 to 4 range, we don't have anything odd. So 1 over 36 is the probability that capital X is 0 and capital Y is 0. Alright, P of 0, 1 is the probability that we get 0 numbers in the 1, 2, 3, 4 range and 1 odd number. So that can happen if we get a 5 and a 6 or a 6 and a 5. So that's 2 out of 36. And then what's little p of 0, 2? So that's the probability of getting 0 numbers in the 1 through 4 range and 2 odd numbers. Well, 5 and 6 are the only things that are left, so I guess that only happens if we get double 5s. So 1 over 36. Alright, let's look for P10. So the probability of getting one number in the 1 to 4 range and 0 odds. So I guess that one number in the 0 to 4 range, in the 1 to 4 range, has to be 2 or 4. So what are the possibilities? 2, but only one number in this range. And then I guess the other one has to be 6, which could happen in two ways, 2, 6 or 6, 2. Or we could have 4, 6, 6, 4. So that's 4 over 36. P11 is the probability that we get one number in this range and exactly one odd number. So if 1 is the number in the 1 to 4 range and there's only one odd number, then I guess the number outside of this range has to be 6. If 2 is the number in the 1 to 4 range, then the number outside that range has to be 5 so that we get exactly one odd number. So 2, 5, 5, 2. If the number in the 1 to 4 range is 3, then the one outside has to be 6 so that we only have one odd. And if the number in the range 1 to 4 is 4, then the number outside the range has to be 5 so that we get exactly one odd. So this is 8 over 36. And now let's look for the probability that capital X is 2 and capital Y is 2. Sorry. Probability that capital X is 1 and capital Y is 2. So one number in this range and 2 odds. So I guess the number outside this range will have to be 5. So this is, we can get 1 and 5 or 3 and 5. And that's it. So 4 over 36. And then the probability of having two numbers in the range 1 to 4 and 2 odds is, well, we can get double 1s, double 3s, or a 1 and a 3 in 2 ways. Those are the only things. That over 36 is 4 over 36. Oh, I just did 2, 2. I put that in the wrong place. So 4 over 36 goes over here. Let's do 2 and 0. The probability that we have two numbers in this range and neither of them is odd. Well, it's almost the same problem actually, because we either get 2 2s or 2 4s or a 2 and a 4 in two different ways. So that's also 4 over 36. So by accident I actually was right, 4 over 36. And then finally, P of 2, 1, the probability that we get two numbers in the range 1 to 4, exactly one of which is odd, is, so we could have 1 2, 1 4, if 1 is the odd number, or we could have 3 2, or 3 4, if 3 is the odd number. So that's what, 8? 1, 2, 3, 8 over 36. So this table gives us the probability mass function for the joint distribution of x and y. Now let's compute the cumulative distribution function. So capital F of xy is the probability that x is less than or equal to this value little x, y is less than or equal to this value little y. So that's the sum over all I less than or equal to this value x and j less than or equal to this value y of p I j. So basically for any entry in this table we're summing everything above and to the left of it. So let's make a new table for the cumulative distribution function. So x is the number in the range 1 to 4, y is the number odd. Alright, so start with 1 over 6 because the only way to get fewer than or equal to 0 numbers in this range and 0 or fewer in that range is to get exactly 0. Then for the 0, 1 entry we take 2 over 36 plus 1 over 36 and get 3 over 36. And for the 0, 2 entry we get 1 plus 2 plus 1, so 4 over 36. For the 1, 0 entry we have 4 over 36 plus 1 over 36, so 5 over 36. For the 1, 1 entry, we have 8 plus 2, 10, plus 4 plus 1, 15. For the 1, 2 entry, we have 4 and 8 and 4 is 16, plus 4 is 20, 20 over 36. For the 2, 0 entry, we have 4 plus 1 over 36, 9 over 36. Here we have 12 plus 12 plus 3, so it's 27 over 36. And here, hopefully we have 36 over 36, because everything is less than or equal to 2, 2. So 4, 8, and 4 is 16. 4, 8, and 4 is 16, 32, plus 4 is 36, 36 over 36. Now there's a very simple relation between the cumulative distribution function and the probability mass function for a single random variable that's a little bit more complicated for 2 random variables. That is, if we want the probability that the random variable capital X is between 2 values, say A and B, let's say possibly equal to B but greater than A, this is f of B minus f of A. If X is the cumulative distribution function of X. But now if we use X to be the cumulative distribution, the joint cumulative distribution function of X and Y, then the probability that X is between A and B, not including A, and Y, let's say A1 and B1, and Y is between A2 and B2, it's not just equal to f of the bigger numbers, B1, B2, minus f of the smaller numbers. The correct formula is that this probability, the probability that X is between A1 and B1 and Y is between A2 and B2 is f of the larger pair plus f of the smaller pair, so plus actually, minus f of the two combinations. So A1, B2 minus f of A2, B1. Yep. All right, so let's see why that would be true. So let's say the x values are a1 and b1. So a1 and b1, and the y values are a2 and b2. So we want everything that's in this range. So just a little bit bigger than a1, just a little bit bigger than a2. I want everything in this range. So if we take capital F of B1, B2, then that's the sum of all the numbers in this probability mass table, or this one. And then if we subtract the lower one, then we're going to get everything except for this region. But that's not what we want. We don't want everything except for this region. We want precisely what's in this region. So the right way to do that is to take the sum of everything in the table, all the probabilities, and then we subtract off, so let's take the sum of the dotted region. So this, the whole thing. And then if we subtract off this region and subtract off this region, then we subtracted off things in this region twice. So the dotted region is f of b1, b2 minus this region, which is f of a1, b2 minus this region, which is f of b1, a2. I put these in the wrong order. And then since we subtracted this twice and we only wanted to subtract it once, we have to add that back in. And that's f of a1, a2. All right, now one more important property of this table for the probability mass function of x and y is that if we sum the rows and sum the columns, the numbers that we get for the sums have important interpretations. So if we sum the rows, we have 1 plus 2 plus 1, 436. And 8 plus 8 is 1636. And again, 1636. And then if we sum the columns, here we have 936. And here 10, 1836. And here 936 again. So if we think about it, this number should be the probability that x equals 0, because it's the probability that x equals 0 and y equals all of its possible values. So this is the probability that x is 0. This is the probability that x is 1, because we're letting y be all of its values. And then this is the probability that x equals 2. Similarly, here we've got the probability that y equals 0. And here the probability that y equals 1. And the probability that y equals 2. So if we're using little p for the joint probability mass function, and we can write p sub capital X for the probability mass function of just x, and little p sub capital Y for the probability mass function of just y. And if we fix, maybe I'll use a different letter here, if we fix a value of little x, and we want this evaluation of this probability mass function, we just sum pay over all possible values of y. And if we want to evaluate the probability mass function for y at just one number b, then we sum over the all values of x with b plugged in for y. These are called marginal probability mass functions. All right, let's look at them just by their definition and see that the numbers we got here by summing columns and rows actually make sense. So we got the probability mass function for just x, evaluated at 0 by adding all the things that we should have. But let's think, what's the probability that x equals 0? We roll 2 dice and we get nothing in the 1 to 4 range. So that's means that we either got 2 5s or 2 6s or 1 5 and 1 6. That can happen in 4 over 36 ways, and indeed we got 4 over 36 here. How could it happen that we roll 2 dice and we only get one thing in the 1 to 4 range? Well, that happens if we get one thing in the 1 to 4 range and one thing in the 5 to 6 range, either the first dice, second die, or the other way around. So that's 8 plus 8, so that's 16 over 36, and indeed we got 16 over 36 here. And how can we get two things in the 1 to 4 range? Well, that's 4 times 4 over 6 times 6, which is 16 over 36, and that's what we got here. All right, let's check the 3 numbers for y also. How could it be that we got 0 odd numbers? Well, you get 0 odd numbers if we get 2, 2, 4, 4, 6, 6, or 2, 4, 4, 2, 2, 6, 6, 2, or 4, 6, 6, 4. So the number of those over 36, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 over 36 is what we got here. How can it be that we got 1 odd number and 1 even number? Well, we get 1 odd and 1 even in 3 ways to pick the odd, 3 ways to pick the even, and then either the odd came first or the even came first. So 3 times 3 times 2 is 18. So that over 36 is 18 over 36, and indeed that's what we got here. And let's look at the marginal probability that y equals 2. How can it be that we got 2 odd numbers? Well, so we either get 1, 1, 3, 3, 5, 5, or some combination of 2 of them. 1, 3, 3, 1, 1, 5, 5, 1, or 3, 5, 5, 3. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 over 36 here. And indeed 9 over 36 is what we got for the marginal probability there. The end.